Hey everyone, welcome back. To all my Eduvos Midrand students tuning in, I know the pressure is absolutely on right now. We are deep into the late 2026 academic year, and those supplementary and deferred assessments, the ones scheduled for September 5th through the 9th, they are approaching incredibly fast. So today's explainer is designed specifically for your BSc IT software engineering module preparation. We are going to completely master section 17.3 of your textbook, Architectural Patterns for Distributed Systems. Okay, let's just dive right in. Here is our cognitive roadmap for today. We'll start with distributed architecture basics, then hit the master-slave pattern, tiered client-server patterns, distributed component systems, peer-to-peer systems, and we'll wrap it all up with a final exam summary.
All right, Section 1, Distributed Architecture Basics.
So in software engineering, you literally cannot just pick a single pattern and expect it to work for every single program out there. It just doesn't work that way. The choice always comes down to the specific, unique needs of the system you're building. When engineers choose an architectural pattern, they base their decision on non-functional requirements. Let's define that really quickly. Non-functional requirements are basically the criteria used to judge the operation of a system rather than its specific behaviors. We're talking about things like performance speed, system security, and manageability. This is a genuinely crucial concept to recognize for your exam. Engineers choose a specific pattern strictly to balance these non-functional requirements. There is no one-size-fits-all. Moving right along to Section 2, the master-slave pattern.
Now, this pattern is absolutely essential for real-time systems. These are systems where strict, predictable deadlines are completely critical. A delayed response here could mean a total system failure. Before we look at how it works in action, let's define the terms. Just think of this as a simple boss and workers analogy. The master is the boss process, right? It coordinates everything, manages the schedule, and assigns the tasks. The slaves are the worker processors. They just put their heads down and execute the heavy computations, or they interact directly with the hardware.
Imagine a traffic management system. It's the perfect way to visualize this boss-worker relationship. Right in the center, you have a master control room that coordinates the entire operation. It sends commands out to the slave processes. On one side, you might have a sensor processor, acting as a slave, gathering data from traffic cameras. On the other side, another slave process directly controls the actual red, yellow, and green traffic lights. The master just ensures they all work together in perfect harmony so we don't end up with total traffic chaos. So just to lock this behavior in your memory for test day, here's your quick recap. You're going to choose a master-slave architecture when you're building real-time systems. Why? Because it offers highly predictable processing. You know exactly which processor is doing what, and that guarantees strict interaction response times.
Okay, Section 3, Tiered Client-Server Patterns.
This is probably the most common way you interact with the internet every single day. We're going to start with two-tier systems, which is the absolute simplest form of this architecture. But look, I want to ensure we're making no assumptions about prior knowledge here, so let's define the foundation in plain English. A client is the receiver of services. That's your smartphone, your laptop, basically the user's computer. The server, on the other hand, is the provider of services. This is the powerful remote computer sitting in a massive data center somewhere, handing out information whenever you request it. It's essentially the internet's digital butler.
Now, here's where it gets interesting and you need to pay very close attention because this is a classic 10-mark exam question for sure. You absolutely must be able to contrast a thin client with a fat client. A thin client puts all the computational heavy lifting on the server. Because the client device is basically just a display, it's incredibly easy to manage and update. But the downside? It generates really heavy network traffic. Now contrast that with a fat client. A fat client does a ton of the processing locally, right on the user's machine. This is great because it saves network traffic, but it is a total nightmare to update. Imagine having to update the software on thousands of individual machines manually.
Just picture how the workload is split across the network. In a thin client model, the client only handles the presentation layer. It's literally just showing you the screen, and the server does everything else. But in a fat client model, the client has absorbed all that application processing too. The server is basically left just managing the database in the background.
A perfect real-world example of a fat client is a bank ATM. The physical ATM machine does a significant amount of local processing to handle your card, securely read your PIN, and run the screen menus. The central bank server just manages the final account transaction at the very end. And hey, let's clear up a massive misconception right now. Fat clients are not some outdated legacy tech.
A lot of modern mobile apps are essentially fat clients because they carry out massive amounts of local processing just to minimize your data usage.
But what happens when you need to grow? A fundamental problem with basic two-tier systems is scalability. So modern web applications, like internet banking, use a three-tier architecture. It separates everything out. The presentation is on the client. The application logic is moved to its own dedicated web server, and the database sits entirely separate on a database server. By separating these into physical tiers, systems can rapidly scale out simply by adding more servers to that middle tier. It's brilliant.
So, summarizing the applications of these architectures is highly testable information. Let's break it down. Thin client is best for data-intensive web browsing where the server does the heavy lifting. Fat client is what you use when you need computationally intensive local processing. Think about running Microsoft Excel, or when your internet connectivity might randomly drop. Finally, multi-tier architectures, those are mandatory for large-scale applications with hundreds of thousands of clients, where data from multiple sources has to be rapidly integrated.
All right, Section 4, Distributed Component Systems.
When you've outgrown strict logical layers and you just need a massive network of independent services talking to each other across a distributed network, you absolutely must have middleware. Let's define it simply. Middleware is the essential software translator. It literally sits in the middle between the operating system and the applications. It manages how different components interact, regardless of what programming language they were written in. This allows incredibly diverse independent components to exchange data efficiently and seamlessly. To summarize this specific pattern, the major benefits are that it's highly scalable and incredibly flexible. It actually allows engineers to delay their design decisions because services can be executed literally anywhere on the network. However, the major drawback? It's highly complex and it lacks universal standards. You'll see this pattern used heavily in data mining scenarios, where resources from totally different retail databases must be dynamically combined to spot market trends.
Next up, Section 5, Peer-to-peer or P2P systems.
In this architecture, those traditional, rigid boundaries of clients and servers, they completely disappear. By definition, peer-to-peer systems are decentralized. Every single computer or node on the network is both a client and a server simultaneously. To use a simple analogy, it's kind of like a store where everyone is both a customer and a cashier. Familiar examples of this include the BitTorrent protocol for file sharing or VoIP apps like Viber, where the overall system relies on the computational power of the users themselves. Now, sometimes you have a semi-centralized P2P architecture. This massive network uses what we call superpeers. A superpeer basically acts as a lightweight server simply to help establish contact, kind of like finding out which of your friends are online in an instant messaging app. Once the superpeer connects you, you and your friend just communicate directly peer-to-peer. Now, I'm pausing on this question because it highlights a critical, high-probability exam point. Why do businesses actively avoid P2P for secure systems? Well, the answer is control. Because P2P completely lacks a central managing server, the network is wide open to malicious nodes. This introduces severe security vulnerabilities, allowing attackers really easy access to deliver spam, malware, or just steal local resources. It's a risk most businesses just won't take.
And that brings us to Section 6, your final exam summary. We've covered a vast amount of technical ground today, so let's initiate our ultimate masterclass recap to solidify exactly what you need to retain when you sit down for your exams between September 5th and 9th. Here are your absolute must-knows. 1. You must be able to contrast the heavy network traffic of a thin client against the management nightmares of a fat client. 2. Understand that multi-tier systems are the standard for web scalability. 3. Know exactly why P2P's lack of central control creates huge security flaws. And 4. Recognize that master-slave architectures guarantee predictable response times for real-time systems. Mastering this foundational knowledge perfectly sets up your next textbook topic, which will be software as a service, or SaaS.
Finally, a really important administrative reminder for all my Midrand students. Please make sure you utilize the new campus paper-cut printing system to print out these visual notes. I highly recommend studying from physical copies to minimize screen fatigue right before the test. Also, keep checking the student portal daily to confirm your exact September 5 to 9 supplementary assessment schedules so you avoid any unnecessary exam day stress. Before you go, ask yourself this. As our everyday devices become increasingly powerful, will the rigid line between client and server eventually disappear altogether? Keep studying hard, and I will see you in the next explainer.